Hello and welcome to physics tutorials. In this video, we shall be looking at the motion of a sphere which rolls down an inclined plane. We'll be studying its acceleration and the time it takes to roll down the plane. We could also study the velocity with which it strikes the ground when it rolls down the plane. Okay, so here we have it. The task before us is to obtain an expression for the time it takes a solid sphere to roll down an inclined plane. And we have a diagram there depicting a sphere that is on an incline that has a vertical height of h, a slant height of x, and that is tilted at an angle theta. Alright, now for us to get the time it takes for this spherical body to roll down the plane, we must consider all the forces at work here. Okay, now the first force we should consider is its weight. I've come up with a diagram here that shows all the forces. The weight acts vertically downwards. Okay, so we have W equals mg. That's the weight. However, this weight has two components. It has a component that is parallel to the plane. Okay, that's the component here. This component mg sine theta. This component is parallel to the plane, while there's a component that is perpendicular to the plane. That's mg cos theta. This one here. Okay. So this is the weight, it acts vertically downward. These are the components. There is mg sine theta, which is parallel to the plane, and then there is mg cos theta, which is perpendicular to the plane. Okay, and then of course there is a force that always opposes motion, and that is frictional force. All right, so since the body rolls downward, it implies that friction would act upward. All right, we'll talk more about that in this video. Okay, and then the mg cos theta component of the weight is not the only component that exists. If it is the only component, then it implies that the sphere would have caused a depression. All right, but then the sphere doesn't cause a depression because there is a component, or because there is a force that acts in the opposite direction to that component of the weight, and that force is called the normal reaction. So these are the forces that act here. There is mg sine theta, there is mg cos theta, there is the frictional force, and then there is the normal reaction. Alright, now let's go ahead and first consider the forces which are parallel to the plane. Okay, if we do that, like we have said, the forces are mg sine theta and our frictional force. So the net force that is parallel to the plane becomes equal to our mg sine theta minus the frictional force. Now there's a minus sign there because both forces are acting in opposite directions. If they were acting in the same direction, then it would have been mg sine theta plus the frictional force. But then they're acting in opposite direction because friction opposes the relative motion between two surfaces in contact. So have our F net equals mg sine theta minus the frictional force. Now let us go ahead and demystify this equation. We know from our Newton's second law of motion that our net force is equal to the product of mass and acceleration. That's to say F net equals ma. So let's insert that in our equation to give us ma equals mg sine theta minus the frictional force. Now let us study the frictional force in this case. For a rolling body, now if this were to be a sliding body, a body that slides down the plane, we could say when the body slides down, the frictional force acts backward, right? But in this case, the body rolls down the plane. It means the friction causes the body to roll. All right? So when the body wants to move down the plane, there's a frictional force between the sphere and the plane. And that frictional force acts in an upward direction and causes the sphere to turn. So the frictional force corresponds to the torque, that's the turning force that acts on the sphere. Alright, so for us to get the frictional force, we're not going to use the traditional method of F equals mu n. No, we have to study the turning force that acts on the sphere. Alright, so let us first take note of this, which is the fact that the frictional force leads to the rotation of the sphere. So we have to study the turning force. Turning force, as we know, is called the torque. Alright, so when we are considering the rotational motion of the sphere, we have that the torque, which is the turning force, is equal to I alpha. Now, torque equals I alpha is simply the rotational version of our F net equals MA. For our linear quantities, we have force, but for our rotational quantity, we have torque. Similarly, for our linear quantities, we have mass, while for the rotational quantity, we have moment of inertia I. Also, for our linear quantity, we have acceleration, which can also be called tangential or linear acceleration, while for the rotational quantity, we have what we call alpha, which is angular acceleration. Okay, so in place of us writing F equals ma, we can write torque equals I alpha. All right, where I, of course, is moment of inertia and alpha is our angular acceleration. So let's take this out and let's go on. So our torque has an expression itself. Torque is equal to the product of force and the radius, okay, r. Here, torque equals r cross f. This means, now this is a vector product of r and f. F, of course, is the force, and r could be several things. R could be the radius or the distance between the force and the line of action or the turning point, okay? And then our sine theta here is brought in when we're considering the scalar components, which means our r cross f is used when we're considering the vector forms, all right? And then our fr sine theta is used when we're considering the magnitudes only, such that our theta is the angle between r and f. All right, now in this case, we know that the angle between the force and the turning point is 90 degrees. While the sphere seeks to move down the plane, the frictional force acts perpendicular to the plane, thus causing the sphere to turn. All right, so the angle between our f and r is 90 degrees. So we'll then take in this expression about torque being equal to Fr. We'll put that into this equation, and that gives us the fact that Fr equals I alpha. Don't forget here, the frictional force is our F, all right? And then for a sphere, the moment of inertia I is given by 2/5 mr squared, while our angular acceleration alpha is equal to our linear acceleration over r. So here we have it. Our F is our frictional force. Our alpha, which is the angular acceleration, is equal to the linear acceleration divided by the radius r, while for a sphere, the moment of inertia is 2/5 mr squared. All right, don't forget our task here is to obtain the time it takes for the solid sphere to roll down the inclined plane. So it's important to us that we keep that in mind, that we're focused on the task. So let us insert these expressions of force, alpha, and I into this equation here, and that gives us frictional force times r equals, in place of our I here, we have 2/5 mr squared, and in place of our alpha here, that's our angular acceleration, we have our tangential acceleration divided by r, that's a/r. So if we play with this mathematically, this r here can take out one of them there, while we can also divide both sides by r for this to take out this, and as such we have only the frictional force being equal to 2/5 ma. All right, so if we do that, we'll have frictional force equals 2/5 ma. I wouldn't just wipe out what we have on the screen. Instead, I'll split my screen so that we can continue and have everything displayed. All right, so now that we have found our frictional force as 2/5 ma, we'll then insert it in this equation for the net force, all right, which gives us ma equals mg sine theta minus 2/5 ma. Now, we can find out that there's mass everywhere, so we can divide both sides by the mass. Okay, divide through by mass, and then we'll have a plus, okay, first of all, we'll have a equals g sine theta minus 2/5 a. So here I have collected like terms, which means I have moved my 2/5 a to the other side, and of course from being negative here, it becomes positive. So I have a plus over 5a equals g sine theta, which means if we add up a with 2 over 5a, that should give us 7 over 5a equals g sine theta. And that implies that a equals 5 over 7g sine theta. Now, from the diagram we have, our sine theta, which is opposite over hypotenuse, is going to be equal to h divided by x, because our h is opposite to the angle while x is the hypotenuse. If we do that, we'll have that a becomes equal to 5gh over 7x. Alright, 5gh over 7x, because our sine theta is h over x. Now, having found the expression for the acceleration, don't forget our task is to find the time. So what connects acceleration and time? We'll have to bring up equations of motion, and the most suitable one for this problem is x equals ut plus half at squared. Alright, where x is the distance covered by the sphere, u is the initial velocity, t is the time it takes the sphere to roll down the plane, and a is the acceleration. Alright, now in this case we're studying a sphere that rolls freely. Alright, it falls freely along the inclined plane, so it is not pushed. As such, its initial velocity is 0, so this part collapses to 0. Alright, and as such we'll have that x equals half at squared. But then again, our a is 5gh over 7x, so we have therefore that x becomes equal to half, and then in place of a we then substitute 5gh over 7x. Alright, that's this, and then times t squared. Okay, so we put that together, we have x equals 5gh over 14. That's 5gh over 14x times t squared. Alright, so next thing for us to do is to make our h the subject of the formula. Okay, so our h becomes 14x squared over 5gh, and for us to get the time which we need, the time becomes equal to the square root of 14x squared over 5gh. In fact, from this first equation up here, we could just find the time directly. Alright, but it's important I bring up this equation because it's a very useful one. In a video I have uploaded, this equation was used to obtain acceleration due to gravity. Okay, we used it as the basis, as a foundation for an experiment to obtain acceleration due to gravity, where our h was plotted on the y-axis and then our t inverse was plotted on the x-axis, and as such our 14x squared over 5g corresponded to the slope from which a known value of x and the slope can give us acceleration due to gravity g. Alright, so we've been able to obtain the expression that we desire. Also take note that we can get the expression for the velocity from here. Y x over t gives us velocity. Alright, displacement over time gives us velocity, and as such we can have this equation become h equals 14 over 5g times v squared. Alright, and then from there we'll have that v, that is the velocity when the sphere strikes the ground, is equal to the square root of 5gh over 14. So we've been able to obtain the expression for the time it takes the body to go down the plane. We've also been able to obtain the expression for the velocity with which the body strikes the plane. If you've learned a lot from this video, I'd encourage you to share with others who are physics enthusiasts, and then like the video and subscribe to the channel so that you can be notified when subsequent videos are released. Alright, have yourself a lovely day.